Differential equations, we're now in section 4.6, day 1. We're going to solve linear non-homogeneous differential equations with a new method. It's called the variation of parameters method, and it's for order 2 for a second derivative in your differential equation. So let's just say that we're going to solve a differential equation that looks something like so. But here's the problem. G of x does not look like any function in the table. So, when we had our table, we were fine. We were doing really well. Let's be honest, that can be a little bit contrived. Who says that the right-hand side must always fit into the table? Well, what do? First, you find y sub c as before. That's with those quadratics. It's pretending that your right-hand side is 0, that you have a homogeneous differential equation. And then you solve with y equals e to the mx. And in general, you get a quadratic, and we solved so many differential equations like that. You'll get a y1. You'll also get a y2. Now, once you get those, the big follow-up is to find the particular solution. We don't have a table to help us, so what we do is we're assuming that there's some function of x, u1, u sub 1 times y sub 1, and add that to u2 times y sub 2. And we're assuming that that's the case. And then we go through these guidelines. We're going to follow this little algorithm. We're going to find the Wronskian. Well, let's have a little reminder what the Wronskian was. It was a determinant. And here are your two solutions that you found via the homogeneous differential equation with that quadratic. You take your two solutions, take their derivatives, work out this determinant. Then you're going to take this equation. If your lead coefficient is anything other than a 1, divide by it, and you're going to see that your right-hand side might change. When you're dividing, you might very well get something different like an f of x. And that's super important that you always make sure that in front of that second derivative, you have a 1 here. Well, once you do have that, this method right here is going to seem very familiar to something that some of you might have studied in Algebra 2, something called Cramer's rule. What you're about to see looks something amazingly like it. You'll see that to find u sub 1 prime, it's w sub 1 over w, where w is the Wronskian, but w sub 1, it's a variation of the Wronskian. You can see it is looking just like the Wronskian, except your one column now becomes 0, and your bottom entry becomes f of x. That's right here, what you just found. Your second row here, y sub 2 and y prime of 2, is the same. But this is what you get solving for u sub 1 prime. Now, solving for u sub 2 prime is something amazingly similar too. You're going to see that it's the second u sub 2, so we go to that second column. And it's the second column that's now different from the original Wronskian. Now it's the second column that has a 0 and an f of x. Your first column, the y sub 1 and y sub 1 prime, are identical to what you saw in the Wronskian. So then what? Well, you've got, for number 5 here, a derivative of u1 and a derivative of u2. So take antiderivatives, and then you'll know what u sub 1 and u sub 2 are. Finally, once you know what u sub 1 and u sub 2 are, then you can find that particular. And then the general solution, well, you know what the general solution is. The general solution is the homogeneous solution, which you always get, from that quadratic work, and then you get your particular solution. So yeah, it's a little bit different kind of a scenario here, but again, we need to have a method to help us when we don't see things working out quite as easily. So let's do an example together real quickly. Just want to point out to you, this is as if you had y double prime plus 0y prime plus y. And just for a moment, pretend that the right-hand side was a 0. And if you were to assume that for this homogeneous solution, you'd have something like y equals e to the mx, it wouldn't take you too long to see that you'd get something like this. M squared technically plus 0m plus a 1. And as we'd solve, we'd get m squared equals negative 1. We'd take our plus or minus square roots, and that would be plus or minus, well, the square root of negative 1 is an I, and this means that alpha would equal 0 and beta would equal 1. And hopefully you do remember that in general what we would see for this homogeneous solution when we're getting complex solutions, it's e to the alpha x plus c1 cosine of beta x plus c2 sine of beta x. And right now, of course, with alpha equaling 0, well, e to the 0x just goes to a 1. And it only is going to work out, beta is a 1, so you'll be able to get this answer for the homogeneous solution very, very, very fast. That's what we're so used to doing, and that's important, of course. Now, from here, we're going to say, you know what? We're going to assume that our particular solution is u1 times the cosine of x plus u2 times the sine of x. I'm getting a little bit ahead of myself right now. I should talk to you about the right-hand side. How now when we're looking at this, because we have a 1 right here, if you went back to the table in our book, our particular solution, we never saw a tangent in that table. So this is a perfect setup where we'd say, gosh, what do we do? I can't start doing the methods that we've been doing just recently. Well, now we're going over what we just talked about. You've got your two solutions coming from the homogeneous aspect. We're going to assume that there's some function of x, u sub 1 times y sub 1 times cosine of x, that is, u sub 2 times sine of x. And then we're going to need the Wronskian. So y sub 1, remember, was equal to cosine of x, and y sub 2 would be the sine of x. And we could go ahead and start working this out. Well, the Wronskian is going to say, well, take your y sub 1 and take your y sub 2 and take their derivatives. The derivative of cosine of x is negative sine of x. The derivative of sine is cosine. And then we go ahead and we cross multiply, and we're going to subtract here. So it's only going to take us a moment to do that. We'll have cosine squared of x minus negative sine squared of x. And of course, that's really cosine squared plus sine squared, which is 1. In other words, our Wronskian is simply a 1. Well, let's go ahead and work out what w sub 1 is. Well, w sub 1, if you went back to our notes here, you can see w sub 1 is where we're going to have 0 and f of x. This is our first column where our first solution normally would be going. So now we're going to have 0 and f of x, where f of x is tangent, isn't it? That's what we're seeing right up here. So we'll have 0 and tangent of x. Our second column is going to remain the same. And as we cross multiply, we'll get, well, 0 times cosine is a 0. Then we'll say minus sine x tangent of x, and of course that's just a negative sine x tangent x, isn't it? Well, then what? We need our w sub 2. W sub 2 keep your first column the same as it was in the original Wronskian. But it's your second column where you'll have 0 and then f of x. And then you cross multiply. You'd say, well, I'm going to have cosine times tangent of x minus, well, anything times 0 is a 0. But tangent, I'm sure you remember, is sine over cosine. And guys, if you're multiplying cosine times sine over cosine, you're just going to get a sine. So this is going to be just the sine of x. So things are working out. We've got this going quite well. We just need to remember a few things. First of all, u sub 1 prime, the derivative, is w sub 1 over w. And w sub 1 was this negative sine of x, tangent of x. And w, you might remember pleasantly, is just a 1, right? So this is nice. It's working out rather well. And tell you what we really want to do is, get this solved for, we'd like to solve for u sub 1, or u prime, I am so sorry. We're going to go ahead and have to take an antiderivative. So let's first do a little bit of work here. We've got, u sub 1 prime. This tangent is sine of x all over the cosine of x. And, as we multiply this through, we'll have negative sine squared of x all over cosine of x. And my goodness, this can look rather bad at first. And we can think, is there something we could do? Well, tell you what, let's look at sine squared as 1 minus cosine squared. And realizing that our ultimate goal is to take an antiderivative, I think that could really help us out. So look, we'll have u sub 1 prime, and guess what? This is a negative 1 and a plus cosine squared of x when we distribute this negative. But we're going to do a little I heart math here too and just divide. And what are we left with? Well, a negative secant of x plus a cosine of x. And that's actually nice because at this point we can say, you know what? We can take an antiderivative. We can take an integral. And the integral of secant, well, it's been a while. It's actually been a little while since we had that. Hopefully you're going to remember. I'll keep the negative out in front. It's the natural log of secant plus tangent. By the way, if you used your TI-89, you'd get that too. The antiderivative of cosine, well, we're just going to write that as a sine. And, wow, I'm going to flip the order here. Just write that as the sine of x minus the ln of the absolute value of secant plus tangent. And you might say, hey, don't we have a constant? You could think of it that way. I'm going to leave it just as is. We don't need the constant as we're working this out. Now look, when we have u sub 2 prime, that's w sub 2 over w. This is way easier, way easier. W sub 2, I think you could see very fast, that's just sine of x, and w is a 1. So we don't have to do nearly as much work here. We can just start integrating. And my word, you'd get u sub 2 is equal to, well, what's the antiderivative of sine? Well, the antiderivative of sine is negative cosine of x. So we have our u sub 1, we've got our u sub 2. Where are we going with this? Well, we're going to go back to what we started with. We're going to say, we found, this setup earlier with the particular that y sub p was u sub 1 cosine of x plus u sub 2 sine of x. And we're going to just work that out, and then we'll know our particular solution. Time's running out on this video. We're almost done, however. We're going to pick